This is the continuation of 5.1. So let's get started with where we left off. So those properties of logarithms I mentioned earlier that we're all supposed to know, where we had the expanded forms of several problems that we did, such as the natural logarithm of a product is the sum of two logs, etc. I'll write them all down. The natural logarithm of a power is the exponent times the logarithm of the base, or natural logarithm of the base, and the natural logarithm of a quotient is the natural logarithm of the numerator minus the natural logarithm of the denominator. Okay, so those are properties that we sometimes will use. And these are actually very convenient to use if we have a function that's really messy looking, that involves things like powers and products and quotients, especially when you have a whole bunch of that stuff going on. Like this example, we have x minus 2 squared divided by the square root of x squared plus 1. And for purposes of having valid answers, we're going to restrict this so that x can't be 2. You'll see why in a few minutes that has to be stated. We could use the quotient rule and find the derivative of this function pretty easily. But what I'm going to suggest we do is something called logarithmic differentiation. And what that means is the first step in logarithmic differentiation is to take the natural logarithm of both sides of the equation. And I'm going to go ahead and rewrite that radical as a power while I'm doing this. And then expand the logarithm of that relatively nasty looking thing. So that is the natural logarithm of the numerator minus the natural logarithm of the denominator. Then those powers are brought down in front. And then we do the derivative of this on both sides. So that's that process we talked about earlier. Not only can you take the natural logarithm of both sides, you can square both sides, you can take the reciprocal of both sides, you can add 7 to both sides. There are all kinds of things you can do to both sides of the equation. And one of the things we added earlier in this course was we can take the derivative on both sides of the equation, and we call that process implicit differentiation. And so I want to remind you of that. So the logarithmic differentiation process itself includes an implicit differentiation step. So we're going to take the derivative on both sides with respect to x. Takes longer to write than it does to say, for sure, especially if I'm not reading the whole thing to you. Okay, and the derivative of the natural log of something is 1 over that something times the derivative of that something, and the derivative of y with respect to x is dy dx. Now on the right side, those are all x things, so their derivatives will just be the normal derivatives we're used to doing, so we won't have to remember to multiply anything by like dy dx or anything. All right, so the derivative of 2 times something is 2 times the derivative of that something, and the derivative of natural log of something is 1 over that something times the derivative of that something. And I'm even going to write in the times 1 here just to clarify that we are using the chain rule. It just didn't make a big difference. And minus the constant 1/2 times the derivative of the natural log of that something is 1 over that something times the derivative of that something, which is 2x. So I would simplify on the right side a bit to make it easier to deal with. So I'm going to just leave the left side of the equation alone for right now. So the first term simplifies to be 2 over x minus 2. And the next one, the 2's cancel, leaving x over x squared plus 1. Now, at this stage, if you wanted to, you could get a common denominator and do the subtraction. And that will lead you to an answer that will look a whole lot like the answer you get using the quotient rule, low d high minus high d low, all over the square of low. But I'm not going to require that you do that, because this right-hand expression could be really nasty looking, and doing the algebra of subtracting those two fractions to me is not worth it. So I'd like for you to just leave that right side alone. Just do the simplification like we did in the prior step, but that's all I want you to do. Now solve this for dy dx. So to do that, we'll multiply both sides of the equation by y. And you could distribute that y, but I'm going to suggest you don't. It's not necessary, and it makes for a messier looking thing anyway. And by the way, sometimes we're setting dy dx equal to 0. So distributing right now would be silly, because you'd have to factor it probably to continue. Now, generally speaking, we want our derivatives to be entirely in terms of x. We have a y in our answer, so we're going to remove that y and put back in its place the original y value, which is the original problem. So I'm going to take the y out, and in its place I'm going to put x minus 2 squared divided by the square root of x squared plus 1. And that will be multiplied by 2 over x minus 2. And by the way, can you now see why the restriction that x can't be 2 at the outset makes sense? We don't want to have x be 2, because then we'd be dividing by 0, and that's not fun. So they wrote that so that we wouldn't accidentally think we could divide by 0. All right, so that is an answer to that problem. Like I said, it's possible that we could have done the distribution. We could have subtracted those two fractions and then done the distribution. I'm just saying that I don't feel like that's necessary for us. It's a lot of extra work, and it doesn't really gain us a whole lot. So I'm going to say let's stop with that problem right there. So as it turns out, that domain issue, like remember we talked about natural log of x squared. X can be anything but 0, but natural log of x can only be a positive number. Because of that, we'll often encounter expressions where we've taken the absolute value of whatever. I'm going to represent whatever with u. And so we're going to deal with y equals ln of the absolute value of u quite often. And so I want to just tell you that, and this is stated in theorem 5.4, that the derivative of that, y equals natural log of absolute value of u, is going to be 1 over u, 1 over the something, times the derivative of the something, which looks just like the derivative of ln of u. As it turns out, the absolute value there doesn't make a difference in our derivative answer. So, for example, if I gave you f of x equals the natural logarithm of the absolute value of cosine of x. And the reason we do this, by the way, is there are a whole lot of x's that create negative answers for cosine. And I don't want to omit those. So by taking the absolute value of that negative number, it turns it into a positive number, and I can take the natural logarithm of that positive number. Of course, there's still numbers I couldn't use. Anything that makes cosine of x equal 0 would be out of the domain still in this problem. But I would gain everything else except for those individual dots on a periodic basis. All right, so let's find the derivative of that. So according to the theorem above, it's going to be 1 over whatever's inside the absolute value. So the absolute value goes away. I want to make that point. Times the derivative of that inside thing. The derivative of cosine x is negative sine of x. And of course, that becomes negative sine of x over cosine of x. And that simplifies to be the opposite of the tangent of x. And there you have it. That's this lesson. I'll see you later.